The mechanisms of plate tectonics. So this kind of a, you guys may not know who Rube Goldberg was, but he was a famous cartoonist who drew these amazing contraptions, you know, and this inspired this drawing by Bob Dietz, who you remember we talked about with the early ideas, and then I think his name was Holden, a gifted artist who just whimsically put these things together, trying to figure out what was making the plates move. But you can see that's pretty humorous. That will not be on the test. All right, so plate motions are well documented. That is for sure. We've got geologic models we've talked about, Nouvelle 1A. Here on this map, we're looking at the yellow red arrows. And then with GPS, the instantaneous plate motions over the last few decades, and from the Revel model, and these are the purple arrows. And they agree pretty well. I mean, two independent systems. Anybody that thinks we're just making this stuff up has got to reckon with these two data sets. But we don't, we haven't really discussed what's causing the plates to move, have we? All right, so most introductory geologies texts explain plate motions as a result of mantle convection. This is a tautology. So here we see the sort of the textbook way it's shown, rising limbs of convection cells and then going sideways, carrying the plates, and then sinking in subduction zones. This is how the introductory geology texts teach it. And I'm going to try and convince you that this is wrong. But it is a tautology. So what is a tautology? When I first ran across that word as a graduate student, I go, what is that? All right, so best way to explain it is by example. So here's some tautologies. I went there personally. Okay, well, how else would you go? She always over-exaggerates. So, always over-exaggerates. I mean, that seems, how do you over-exaggerate? Maybe that's not good tautology, but it certainly is not very clear speaking. In my opinion, I think he is wrong. Okay, of course it's your opinion. You think he's wrong. I mean, now Bon Jovi perhaps has the most famous one. I want to live while I am alive. Now that is admirable, but it's in fact the only time you can live. After you're dead, you will not be able to live. Well, we just came through Easter, so okay, I don't want to insult anybody's religious tendencies. But for those of us that are less impressed with the afterlife, you kind of have to live while you're alive. And then the last one is the plates move because of mantle convection. So, the plates are I will try and show you that the plates are the expression of mantle convection. They are not moving because of mantle convection. And that may be a bit confusing. All right, so let's back off and think about this a little bit more. What makes the plates move? So we're somewhat in the position of Native Americans when they first encountered a steam locomotive. They must have quickly figured out the locomotive pulled the rest of the train and that the locomotive moved because the wheels rotated. But that's a purely kinematic description of motions, right? We've talked about the difference between kinematics and dynamics before, but the Native Americans couldn't possibly understand the dynamics of a steam engine, and nobody could until they were trained in it. So what we need, if we really want to understand what's going on, we need a dynamic description for both the locomotives, in this case, or mantle convection. And in both cases, we have to consider the role of heat. Heat is important. So here's a dynamic description of a steam locomotive, which is a heat engine. So in fact, what you do is you put coal in here and you burn it and it heats up coils of water, and that water turns into steam, and that steam moves a piston back and forth that drives the wheels. That's what's happening. That's a better, this is perhaps a kinematic description of a locomotive. This is more of a dynamic description. All right, let's watch a video. Can you hear it?
This is the big picture.
We once thought that mantle convection
I could see it, but not hear it. Oh, now I can hear it.
Tectonic plates
Early
could drive
textbooks
plate
showed
motions.
mantle convection cells
Early
like
textbooks
in a beaker
showed
of
mantle
hot liquid
convection
on a Bunsen
cells,
burner,
like in a beaker of
pushing
hot
plates
liquid on a
along
Bunsen
from
burner, pushing
Current
plates
dynamic
along from
models have
below.
plates moving as part of a
Current dynamic
gravity-driven
models have
convection
plates moving
system
as part of a
that
gravity-driven
pushes young
convection
hot plates
system
away from spreading
that pushes
ridges
young hot
and
plates
pulls
away
old
from
cold
spreading
plates
ridges
down into
and
subduction
pulls
zones.
old cold plates down into subduction zones.
Remember that lithospheric plates, also called
Remember that
tectonic plates,
lithospheric plates,
have a layer
also
of
called
crust on
tectonic
top
plates,
of lithospheric
have a
mantle,
layer of
the
crust on
outermost
top of
rigid part
lithospheric
of
mantle, the
These
outermost
move
rigid
as
part
a
of the
single
mantle.
unit.
These
The
move
hotter
as a
asthenosphere
single
beneath
unit.
the plates is
The
solid,
hotter
but less
asthenosphere
rigid
beneath the
mantle
plates
rock
is
that
solid,
can
but
slowly
less
flow.
rigid mantle rock
Now
that
let's
can
look at the
slowly
broader
flow.
picture. This
Now
map
let's look at
shows
the
how
broader
seafloor
picture.
increases in
This
age
map
with
shows how the
distance away from
seafloor
spreading
increases in
ridges,
age with
such as the
distance
East
away
Pacific
from spreading
Rise or the
ridges,
Mid-Atlantic
such as the
Ridge,
East Pacific
where new
Rise
ocean
or the
plate is forming.
Mid-Atlantic Ridge, where
Spreading
new
ridges
ocean plate is forming.
stand 2,500
Spreading
meters
ridges
higher
stand
than deep ocean
2,500
basins.
meters higher
At a
than
spreading
deep
ridge,
ocean
the
basins.
ocean depth is
At a
only
spreading
about
ridge,
3,000
the
meters.
ocean depth is only about
Ocean depth
3,000 meters.
increases with age of the
Ocean depth
underlying plate,
increases with
so that
age of
where
the
the plate is
underlying
more than
plate,
80 million
so that
years
where the
old,
plate is more
the
than 80
overlying
million
ocean
years old,
increases to
the overlying ocean
5,500 meters deep.
increases to
Let's examine the
5,500
formation
meters
of
deep.
new oceanic
Let's
plate
examine the
and how that
formation
plate
of
cools
new
with
oceanic
age.
plate and how that plate
As hot
cools with
mantle rock
age.
rises to lower pressure,
As hot
a
mantle
small
rock
portion
rises
of
to
this
lower
upwelling
pressure,
asthenosphere
a small
melts
portion
to
of this
form magma
upwelling
that builds
asthenosphere
7
melts
kilometer
to
thick
form magma
oceanic
that builds the
crust
7
at the
kilometer thick
edges of
oceanic
diverging
crust
plates
at the
along the ridge
edges of
axis.
two diverging plates along
Beneath
the ridge
crust at the
axis.
spreading ridge, there is only
Beneath
a
the
thin
crust
layer
at the
of
spreading ridge,
lithospheric mantle
there is only a
because
thin
it is
layer of
unusually
lithospheric
hot in the
mantle
upwelling zone.
because it is unusually
This
hot in the
and
upwelling
therefore
zone.
lower density
This
mantle
hot
rock
and therefore
supports the
lower density mantle rock
2,500 meter elevation
supports
of
the
the spreading ridge.
2,500 meter elevation
As
of
the
the
plate
spreading
slowly
ridge.
moves away from the ridge,
As the plate
it
slowly
cools by
moves away from the
conducting heat
ridge,
through the
it
crust
cools
to
by
the
conducting
cold
heat
ocean
through the
water
crust
above.
to the cold
At the same
ocean
time,
water
the
above.
underlying
At
asthenosphere
the same
cools
time,
and
the underlying
adds to the bottom of the
asthenosphere cools
lithospheric plate.
and adds to the
Thus,
bottom of the
although the
lithospheric plate.
crust maintains its
Thus,
thickness during
although the
migration away from
crust
the ridge,
maintains its thickness during
lithospheric
migration
plate
away from the
thickens
ridge,
and
the
cools
lithospheric
to
plate
create ocean
thickens
basins
and
that
cools
extend
to
5
create
kilometers
ocean
in
basins
depth.
that
A
extend
simple
5
way to
kilometers
think about
in depth.
elevation
A
is that
simple
the
way to
plate
think
is
about
young,
elevation
hot, and
is that the
high
plate
at the
is
spreading
young,
ridge
hot, and high
becomes old,
at the spreading
cold,
ridge
and low
and becomes
during the
old,
aging
cold,
cooling
and low
process.
during the aging and cooling
Mathematical modeling
process.
of this cooling process illustrates
Mathematical
the ocean
modeling
plate
of this
becoming
cooling process
cooler and
illustrates
thicker
the
with
ocean
age.
plate becoming
The
cooler and
temperature
thicker
at
with
the bottom
age.
of the plate is
The
about
temperature at the
1,300
bottom of the
degrees
plate
centigrade.
is about 1,300
Notice that
degrees
most
centigrade.
of the cooling process
Notice
occurs
that most
between
of the
age 0
cooling
at the
process
ridge
occurs
and about
between
80
age
million
0 at the
years when the
ridge
ocean plate
and
has
about
grown
80
to
million
about
years
100
when the ocean
kilometers
plate
thick.
has grown to about
The upper
100
plate
kilometers
is
thick.
less than 600 degrees
The upper
centigrade.
plate is less
Thus
than
is the
600
only
degrees
part of the
centigrade.
plate cold
Thus
and
is the
brittle
only
enough
part of the
to
plate
fracture and
cold
produce
and brittle
earthquakes.
enough to
Though
fracture
still
and
rigid,
produce
the
earthquakes.
lower plate is warmer
Though still
and
rigid,
can
the
deform
lower
in a
plate is
ductile
warmer
or plastic
and can
fashion.
deform in a
So
ductile
what
or
force
plastic fashion.
pushes oceanic plates
So what
away from
force
spreading ridges?
pushes oceanic plates
Any
away
mass
from
on a
spreading
slope
ridges?
is affected by gravity,
Any mass on
seen
a
most
slope is
dramatically with
affected by gravity,
avalanches and
seen most
landslides.
dramatically with
Spreading
avalanches and
ridges are
landslides.
broad undersea mountain
Spreading
ranges,
ridges are
and
broad
although the
undersea
flanks of a
mountain
spreading ridge
ranges,
are a
and
relatively
although the
gentle
flanks of a
slope,
spreading ridge
the
are a
mass on that
relatively
slope
gentle
is
slope,
humongous.
the mass on
The
that
force
slope
of
is
ridge push
humongous.
is zero at
The
the
force
ridge,
of ridge
but
push is
increases
zero
quickly
at the
with
ridge,
distance
but
and age,
increases quickly
pushing the
with
cooling
distance
and
and
thickening
age,
oceanic
pushing the
plate
cooling
away from
and
the ridge.
thickening oceanic plate
Now what
away
about
from the
slab
ridge.
pull?
Now what
We'll
about
consider a
slab
30
pull?
million year old
We will
oceanic
consider a
plate,
30
which we'll
million
call a
year old
slab,
oceanic plate, which
subducting
we'll
at
call a
5
slab,
centimeters per year
subducting
into
at
hotter
5 centimeters
asthenospheric
per
mantle
year into
beneath the
hotter
convection
lithospheric mantle beneath
As
the
the
continental
oceanic
plate.
plate subducts,
As the
warming
oceanic plate
process takes
subducts,
many millions of
the
years
warming
as the
process
slab
takes many
descends.
millions of years as the
deeper
slab
part of it
descends.
is
The
continuously
deeper
replaced
part of it
in a
is
conveyor belt
continuously
fashion
replaced
by
in a
cooler plate
conveyor
from
belt
above.
fashion by cooler
Mathematical
plate from
modeling
above.
again illustrates the
Mathematical
temperatures
modeling
within the
again
subducting
illustrates the
oceanic
temperatures
plate.
within the subducting
In this
oceanic plate.
example, lithospheric mantle
In this
rock in the
example,
subducting plate
lithospheric
at
mantle rock
150
in the
kilometers
subducting
depth
plate at
is
150 kilometers
1,000 degrees
depth
cooler
is
than the
1,000
asthenospheric
degrees
mantle at the
cooler
same depth.
than the asthenospheric
The
mantle
cooler
at the same
temperatures
depth.
mean that the density of
The
rocks
cooler
in the subducting
temperatures
slab
mean that the
is
density
greater
of rocks in
than
the
the density
subducting
of the
slab
hotter
is greater
asthenosphere.
than the density of the
While
hotter
gravity pulls
asthenosphere.
down on all rocks,
While
it
gravity pulls down on
harder
all
on
rocks,
more dense
it pulls
rocks.
down harder
This
on more
enhanced
dense
gravitational
rocks.
force on the
This
cooler and
enhanced
denser rocks
gravitational
in the
force on the
subducting plate
cooler and
is the
denser
slab
rocks in the
pole
subducting
gravity
plate
force.
is the slab pole gravity
Earthquakes,
force.
including great megatrust
Earthquakes,
earthquakes,
including
occur on
great
the shallow
megatrust
part of the
earthquakes,
boundary between
occur
the
on the
converging
shallow
plates
part of the
and
boundary
within the
between the
shallow parts
converging
of
plates
both plates
and
near
within
that
the
boundary.
shallow parts of both plates
In
near
addition,
that boundary.
there is a zone of rock
In
cooler
addition,
than
there
600
is a
degrees
zone of rock
Celsius
cooler
within
than
the
600
subducting
degrees
plate that
Celsius
remains brittle
within the
and within
subducting
which
plate that
earthquakes can
remains
occur
brittle
to
and
depths of
within which
hundreds of
earthquakes can occur
kilometers.
to depths of hundreds
Observations
of
of interplate
kilometers.
earthquakes and other
Observations
indications
of
of stress
interplate
with tectonic
earthquakes and
plates
other indications of
suggest that
stress
the
with
slab
tectonic
pole
plates
force
suggest
is
that the
usually
slab
larger
pole
than the
force
ridge push
is
force.
usually larger
It is
than the ridge
noteworthy
push
that
force.
fast-moving plates,
It is
like the
noteworthy
Pacific
that
plate,
fast-moving plates,
generally have a
like the
fast
Pacific
spreading
plate,
ridge pushing
generally
on one
have a
side,
fast
while the
spreading ridge
subduction
pushing
zone
on one
pulls on
side,
the other side.
while the subduction zone pulls on
In
the
this
other
big
side.
picture view, we see that
In this
lithospheric
big
plates
picture
are
view,
part of a
we see that
planetary scale
lithospheric
thermal
plates are part of a
convection system.
planetary scale
The
thermal
energy source
convection
for
system.
plate tectonics is
The
Earth's
energy source
internal
for plate
heat,
tectonics
while
is
the
Earth's
forces
internal
moving the
heat,
plates
while
are
the
ridge
forces
push
moving the
and
plates are the
slab
ridge
pull
push
gravity
and slab
forces.
pull gravity forces. So far, we've illustrated these motions on a flat image that may suggest that there is only a handful of convection cells turning like gears in a flat plane. As a result, it may look like these movements only occur in small regions.
That's pretty good video. That explained it way better than I learned in college.
Yeah, and you can see that the production values on those, that was done by a professional videographer. Yes.
My only thing I didn't really understand in that, Clint, you explained it pretty good to me, period, about 6 weeks ago, but I don't understand how at one point the 600 degrees C, and then as the plate enters and subducts, it drops to 350 degrees C, even though it's deeper. I mean, how's it cool?
Well, no, that they're just showing different isotherms. So you can imagine that a plate has a set of isotherms from basically zero at the top at the seafloor down to 1300, the base of the lithosphere. And we've talked about the mechanical lithosphere versus the thermal lithosphere, right? The mechanical lithosphere is the one that can break. So that's what the 600 degrees about. The model that you saw was not there to suggest that 600 degrees turns into 350.
Gotcha.
They were just using 350 sort of as an indicator of how the how the isotherms in the plate were deflected in the subduction zone, because you're carrying this cold material down to great depth. So that was that they're not they didn't that might have been a flaw in the representation. Because what you're right, things heat up as they're eventually the slabs will heat up, right? But at first they still relatively cold compared to the surroundings. All right, so let's consider this. We talked about a locomotive. Let's talk about a yes.
So I have a question. Yeah.
Sure.
Okay. So from this video, it's okay to say that the causes of plate tectonics is ridge push and slab pull.
Yes, that's what's driving the plates. Yes, and we'll talk more about that. That's not the last time we'll talk about it today.
Okay. Thank you.
All right, so let's consider another heat engine. So here we're just looking at patterns of global heat flow represented by spherical harmonic analysis with a contour interval of 40 milliwatts per meter square. And you can see the regions of very high heat flow are centered on the spreading ridges, right? There's the East Pacific rises sitting there. right? It's a very smooth thing. So mean oceanic heat flow is 67 milliwatts per meter squared. Mean continental is about 65. And remember, we talked about seafloor heat flow versus age, and the fact that we couldn't really measure it near the ridges because it's dominated by hydrothermal circulation. So what's happening? The lithosphere is increasing in density, pulling seafloor down. So that is telling you that the seafloor density is increasing as the plate ages, right? And here we can see that a little bit better. I generated this a few years ago for teachers, and basically it's to explain what's driving the plates. So what the paper is called A Subduction Primer for Course Instructors and Authors of Introductory Geology Texts, in the hope that we could convince some of them to present the dynamical causes of plate motions better. So here we're looking at 3 slices through oceanic lithosphere. One is right at the ridge. One is 10 million year old oceanic lithosphere, and the other one is 100 million year old oceanic lithosphere. And now, so here we've got the mantle lithosphere right at the ridge is 0. It's basically, basalt on top of a asthenosphere right at the ridge. So that means that the mantle lithosphere is 0% of the total lithospheric mass. So the density of the lithosphere is that of the density of the basalts, which is 3 grams per centimeter. Now, the mantle asthenosphere is thought to have a density of about 3.25 grams per cubic centimeter. So 3 grams per cubic centimeter is much less than 3.25. So this is gravitationally stable. This floats, if you will, on top of the asthenosphere. So this is buoyant lithosphere. It'll resist subduction. And let's go to 10 million year old oceanic lithosphere. And we can model the thickness of the mantle lithosphere as the mantle lithosphere thickness is 10 times the age to the square root of age. So at 10 million years, the thickness would be what? 31.6 kilometers thick. That's just the math. 10 times I guess the square root of 10 is 3.16. So the lithosphere density, lithosphere thickness is crust plus mantle. It would be 37.6, right? 6 kilometers plus 31.6. The mantle lithosphere is 84% of the total lithospheric thickness, which gives it a density, multiplying 84% by mantle lithosphere times that, plus 16% times that, comes up to 3.25 grams per cc, which is exactly the same as the asthenosphere. So the density of the lithosphere in this case is equal to that of the asthenosphere. So it's neutrally buoyant. It doesn't sink or float, really. Now, out at 100 million years, the mantle lithosphere is thickened greatly. So if the square root of 100 is 10, so 10 times 10 is 100 kilometers. So that's a 100-kilometer mantle lithosphere, plus 6 kilometers of basaltic crust. The mantle lithosphere is 94% of the total lithospheric thickness. So we get a density of the lithosphere of 3.28. So in that case, the density of the lithosphere is greater than the density of the asthenosphere. So it wants to sink. That's only a 1% difference in density, but that's enough. It's negatively buoyant. It wants to sink. And it's the great strength of the lithosphere that keeps it from sinking as soon as it reaches negative buoyancy. And it has to wait until it can come to a subduction zone to go down. Okay? So that's basically what's going on with density as a function of age. Is that reasonably clear? Not, we certainly can discuss it. It's central to this discussion. All right, so here's a continental heat flow map. This was done. Yes, somebody had a question?
I was just going to say, you did use the R word there, right? Rheology?
Yes, the rheology of lithosphere prevents it from sinking because,
So
100 kilometers of solid rock is going to be fairly strong, and we know very well, if you have water, it can drip, but steel can't drip. So if you throw, let's say, a balloon full of lead in your swimming pool, it will sink easily because water, the rheology of everything allows it. But if you throw a sheet of steel in your pool, it will sort of slide. It has to slide sideways in order to sink, which it will. But yeah, rheology is a big part of this. Now, this is an important contribution from Dallas. This is the SMU geothermal lab, which Dave Blackwell ran. He retired, and I'm not sure what's going on there now, but they generated this remarkable map of heat flow in milliwatts per meter squared across the United States. And the blue regions are where it's relatively cold. Here with the Cascadia margin, as we expect, forearcs will be cold, and it is. And then once you get to the volcanic arc, the Cascade Arc, you can see the heat flow goes way up. The Western United States has a relatively high heat flow. Interestingly, parts of Texas, Louisiana, and southern Arkansas also have moderately high heat flow.
Well, just one of those rabbit holes I love to go down, but why is that? And plus, what's the high heat flow in South Dakota, right next to kind of southeast of the Black Hills? I don't understand that.
Yeah, that's a good question. There's something interesting going on in South Dakota, and that would make an interesting research project for somebody. Yeah, there are some interesting features in this. All right, so this is the conductive heat flow in oceans, continents, and total. And so this was one of the original observations that made people puzzle. It's like, why would the heat flow in the oceans and the continents be so similar? And it basically adds up to the global heat flow. You can't really tell. Obviously, in mid-ocean ridges, you have very high heat flow out here. And then as the oceans age, the heat flow decreases. And what the community decided was this heat flow is coming from the very thin young lithosphere, but the continents, they have, this is a lot of radioactivity going on that's contributing to this, and it just happens that way. All right, so oceanic heat flow indicates that heat is flowing from the hot interior, which is the asthenosphere, through the cold exterior, which is the lithosphere. So what are the implications of colder lithosphere on top of hotter asthenosphere from mantle convection? So for this, we have to talk a little bit about some material science. And this has got to do with the coefficient of thermal expansion called alpha, which describes how volume of a solid changes with temperature. So alpha is sometimes called alpha sub V, right? So it's defined as 1 over V times the partial differential of volume with temperature at constant pressure. So if alpha is greater than 0, the same mass at higher temperature occupies more space than at lower temperature, right? So if the volume increases with temperature, that's going to be positive. Let's watch a video.
Story now you asked us to investigate. A concerned viewer sent us this picture. We'll give you a close look at it. And it shows what appears to be a crack in the flyover on I-15 near Spring Mountain. We reached out to NDOT. They tell us that's not a crack. It's an expansion joint that lets the concrete expand and shrink for changes in temperature and protects the bridge during earthquakes. We looked into this story after a viewer posted it on Facebook. If you have something you want us to check out, send an email to 13investigates@ktnv.com or put it on our Facebook page like she did. And please be sure to include your name and phone number.
Concrete is basically a rock, right? So if you were building bridges you definitely want to know what the alpha for concrete is so that you could, make those expansion joints right. If you didn't put a thermal expansion joint in, you could break the bridge, right, in a hot day. And the alpha for concrete is about 10 times 10 to the minus 6 per degrees centigrade. It's not much, but still significant if you have a large volume of concrete.
Now you ask.
All right. So because density is a function of 1 over a volume, if the coefficient of thermal expansion is greater than 0, then hot mantle is less dense than cold mantle of the same composition. So let's consider this. Peridotite alpha is about 3 times 10 to the minus 5. It's a little bit larger than that for concrete, but nothing dramatic. So how much denser is peridotite if it is at 1200 degrees centigrade than if it is at 400 degrees centigrade? And remember, the nominal density of peridotite is around 3.3 grams per cubic centimeter. So let's just run the numbers. So this delta volume is alpha times delta T. So that's the coefficient of thermal expansion. And the difference in temperature between 1200 and 400 is 800. So 800 times that, it comes about 2.002.024, which means it's about 2.4% larger. So, that's the difference in volume. Hot asthenosphere of the same composition is about 2.5%, takes up 2.5% more space than equivalent composition lithospheric mantle. So if the solid of fixed composition occupies 2.4% larger volume, then it must be 2.4% less dense. So what that means is if we have cold lithosphere on top of hot asthenosphere, it's gravitationally unstable. And that's going to want to change positions, right? Any questions about that? And you won't be asked to calculate this on the midterm, but it is kind of nice to know a little material science and why when you go over a freeway bridge it's always bumpy. You're going over those expansion joints, if not potholes. All right, so we know that heat's flowing from the hot asthenosphere through the cold exterior. So these things are going to want to change position. Now, how does it do that? Now, your book talks about thermal boundary layers, and this was always kind of a complicated thing for me to understand when they use thermal boundary layer, because we use it interchangeably with lithosphere. So a thermal boundary layer is basically a blanket. So like when you're in the wintertime, your body is a convecting media, right? The same temperature everywhere. And the air is convecting. And between the two, right, the air, maybe in your house is 65 degrees at night and you're at 98 degrees. And you want to keep as much of that 98 as you can. So you put a thermal boundary layer on between you and the air. That's called a blanket is a thermal boundary layer. And so the lithosphere is Earth's blanket. And that's the way to think about it. So the book talks about the behavior of thermal boundary layers. And here we have 3 behaviors. Here we have a cold, it's cold on the outside, hot on the inside. That sounds like the Earth. And here's this thermal boundary layer, which we've already said is denser than the underlying material. So here the book's showing it sort of dripping off, kind of like a drip from your ceiling when your upstairs neighbor has flooded his bathroom, right? It's showing it as a drip, which that doesn't look like Earth, right? That doesn't look like a subduction zone. The density structure is like a subduction zone, but the physical appearance of drips are quite different than sheets like subduction zones. And this is the temperature profile associated with that. And in fact, there's another boundary layer here. So this is the core, which is hotter than the mantle. So you've got another boundary layer here, and it's rising for the same reason that this is sinking, the coefficient of thermal boundary of expansion, right? So you've got two things happening. One is cold material sinking, hot material rising. Now, in this one, your book shows this with only a cold thermal boundary layer on top. And the internal heating is keeping this temperature gradient down, so there's no thermal boundary layer between the core and the base of the mantle. And then this one is showing you something like that, but because there's internal heating, there's not as much of a boundary temperature difference between this and this. So you don't have the big upwellings, you have small upwellings. Okay? Does that make sense to anybody? This idea of thermal boundary layers is very useful in understanding Earth and other planets. All right, so then your book starts talking about the physics of mantle convection, and we're going to talk about three things. One is we're going to talk about Rayleigh numbers, then we're going to talk about Reynolds numbers, and then we're going to talk about Nusselt numbers. And this is physics, but it's fairly simple physics. So let's talk about Rayleigh numbers first. The Rayleigh numbers considers the likelihood of convection. So this assumes a Newtonian fluid. And what we mean by that is a fluid whose stress versus strain curve is linear and passes through the origin with a slope that is defined by its viscosity. So, you know, it's sort of a physical abstraction. It doesn't really matter, but that's what they talk about. So whether or not convection happens depends on the Rayleigh number, and that's denoted R sub A. And that is the ratio of buoyancy forces to resisting forces. So if you think about the mantle, you know, there's a buoyancy force of hot material wanting to ride, and there's resisting forces of the strength of the material it's trying to rise through, right? So the equation, the Rayleigh number is equal to alpha. We've seen that. That's the coefficient of thermal expansion times the density. We know what that is, times the temperature difference. You know, in the convecting mantle, that's the adiabatic temperature gradient, times the gravitational acceleration, times the thickness of the layer to the fourth. So that's a huge control on the Rayleigh number, divided by the coefficient of thermal diffusivity, the ability of heat to be exchanged through the material, and the viscosity, right? The higher the viscosity, the harder it is to convect. So, according to this simple physics, for convection to occur, the Rayleigh number must be greater than 1,000. And plugging these numbers in by people that know how to do that, these are geodynamicists, Earth's mantle Rayleigh number must be is considered to be on the order of 1 million, which is a lot more than 1,000. So according to these considerations, Earth convects. Earth should convect. Is that clear? It's a very simple calculation if you're a physicist. If you're a geologist, yeah, struggle with it maybe a little bit more, but I think the concept is clear. Any questions on that, on Rayleigh numbers? All right. Then the next question, if convection occurs, will it be laminar, like plate tectonics, right? Or will it be turbulent, right? Here's turbulent. I think everybody's sort of familiar with laminar flow versus turbulent flow. You see that in hydrology a lot. But, you know, just having the realization from the Rayleigh number that convection is likely, it doesn't tell you whether it's going to be turbulent or laminar. So, you know, turbulent convection might be like a boiling pot of water on your stove, right? You don't know where the next bubble's coming up. And laminar, though, is very much plate tectonics. Plate tectonics is a kind of laminar convection. So this brings us to the Reynolds number. So if convection occurs, according to the Rayleigh number, then we look at the Reynolds number to determine whether convective flow is laminar or turbulent. So the Reynolds number is just the velocity of the convection times the thickness of the convecting layer, fluid layer in this case. It's always funny to me when I realize that the geodynamicists talk about treat the mantle as if it was a Newtonian fluid. So I was in Switzerland at a very famous institute, ETH. It's sort of the Caltech of Europe. And they have a department of geophysical fluid dynamics, which is about how the mantle flows. And I looked at that one day and I go, that's ridiculous. The mantle is solid. Why would they be using fluid dynamics? But that's the way we're able to model the mantle as an extremely viscous fluid. But okay, back to the Reynolds number. The Reynolds number is equal to the velocity of convection times the thickness of the layer divided by the viscosity, right? Viscosity is always going to be impeding convection. But for low Reynolds numbers, you expect laminar flow. And for high Reynolds numbers, turbulent flow is expected. So Earth's mantle Reynolds number is about 9 times 10 to the minus 20. So, a billionth is 10 to the minus 9. So this is, less than a billionth of a billionth. So the Reynolds number is extremely low for Earth, which means laminar flow is expected. And that is consistent with plate-like convection. Okay, those are very simple physical considerations, but useful. And then finally, let's get to the Nusselt number. The Nusselt number determines the ratio of total heat transported by convection to that transported by conduction. At a Rayleigh number corresponding to marginal convection, the Nusselt number is 1. So if the Reynolds number is less than 1, then the heat's can transfer by, I think maybe I've confused myself here. I think it's got to be the Nusselt number, that where I wrote RE there, less than 1, that should be NU. So I apologize for that. At NU less than 1, heat's transferred by conduction. At NU greater than 1, heat's transferred by convection. So at the Reynolds number for Earth's mantle, the Nusselt number is about 100, which means that convection is very efficient. Okay, so those are the physical considerations for Earth's convection. So Earth's mantle is likely to convect just by these considerations. The Rayleigh number is very high, which says that convection is likely. The Reynolds number is very low, which means there's got to be laminar flow if it's convecting. And the Nusselt number is high. So convection is an efficient mode of heat transport. But none of this requires plate tectonics, which is a special type of convection. Okay, that was a lot of material, but I hope made sense. So we've talked a bit about this. This is kind of how I see the planet, silicate planet evolving, with it cooling and the lithosphere thickening and strengthening. And we'll see this again. All of these stages show some convection with hot, buoyant asthenosphere rising and cold, dense lithosphere sinking. Here we see sinking drips. Here we see, bigger drips. And here we see plate tectonics. These are all modes of convection. Now, we are confident that Earth's mantle convects, but we're not sure about very many details. So for example, there's a discussion about, is the entire mantle convecting like this, what we call whole mantle convection, or is it segmented, right? We talked about the mantle transition zone between 410 and 670 kilometers. And some people think that that separates convective realm, with the lower mantle convecting separate from the upper mantle. So what is the relationship between plate motions and convection? Now, we've seen these seismic tomographic images, and they make you think about convection. You're going, oh, that looks like something's rising from near the core mantle boundary, you know, and that looks like something's sinking, right? Here we see other things sinking. They're not, we don't really know how these things are moving, but in your imagination, you almost see them moving. So now let's get, okay, we don't really understand why there's plate tectonics, but once we have plate tectonics, we can do simple force balances to try and figure out what's making it move. So this is, it looks like about 10 different forces that are operating on the plates. Oh, let's see. I say 9 there, don't I? So here's 4, and here's 6. So it looks like that should be 10. I apologize again. So what we've got here is ridge push. That's the ridge push, the downslope movement of the lithosphere due to gravity. There's the negative buoyancy of the subducting slab, FNB, which is vertical. There's slab pull, FSP. Where is it? There we go. And there's trench suction. You're probably wondering what that is. We'll talk about that a bit. Those are the forces acting on the plate, and then these are the resistances. There's the ridge resistance. There's the bending resistance here. There's the slab resistance, right? The slab is sinking into the mantle, and the mantle is resisting that. There's the overriding plate resistance, the friction between the two plates. Then there's mantle drag under the oceans, and there's mantle drag under the continents. So let's talk about the ridge push force. So it's been modeled in 2 different ways, as a body force and as a boundary force. We probably don't have to spend too much time on that. Just to understand that the ridge push force is focused on this slope of the lithosphere. And we can calculate that. So that can be calculated by the pressure head. F ridge push is equal to gravity times the density of the mantle times the difference in elevation minus the density of water and its thickness. And then you plug in some numbers and you come up with a force on the order of, here's one estimate of 2.4 times 10 to the 12th Newton per meter. Another calculation, 3.9 times 10 to the 12 Newton per meter. So somewhere in there is the ridge push force. The slab pull force is the force directed along the length of the subducted lithosphere, FSP. And it's relative, this difference in density is relatively small at shallow depths, and it changes because of the metamorphism of the slab. And the slab pull force depends on the dip of the subducted slab, the length of it, the age of it, and the temperature difference between the slab and mantle, which controls the density differences. And you plug in the same sorts of things. The slab pull is equal to gravity times the length times the difference in the depth and the difference in density, and you come up with a slab pull on the order of 3 to 5 times 10 to the 13 newtons per meter, right? That's an order of magnitude bigger than the ridge push. And, you know, the point is not the exact number, but the fact is that the slab pull force is an order of magnitude greater than the ridge pull force. So when people ask me what's driving the plates, I'll say it's 90% slab pull and the other forces associated with the slab sinking in the subduction zone, and 10% ridge push, right? And other people will have slightly different, but that's the geodynamic consensus, is that it's 90% slab pull that's driving the plates. So let's watch a video. So that's pretty simple-minded experiment, but you know, that is in a nutshell what the geodynamic community thinks is going on to drive plate motions. The plates are being pulled by subduction zone, by the slab sinking in subduction zones. Now, this is a slight diversion, but we're talking about trench rollback. So you may think that subduction zones are zones of compression, and locally they are when you're subducting very young oceanic lithosphere. But in more generally, they're not. And what that is telling you is something very interesting. So this brings up the concept of trench rollback. So the idea is that, okay, if we had a subduction zone where the lithosphere was being subducted down dip, right? See the angle there? Then we would not expect the overlying plate to move in this direction. And that's what we're seeing here. So there's 5, and then with time it continues, and the trench stays fixed. So here there's no slab rollback. On the other hand, if the slab is sinking more steeply than the Wadati-Benioff zone indicates, like this, it's going to pull the overlying plate towards the ocean. So there we are at the beginning, and then after a while we've got this, and then this. So this one is experiencing slab rollback. Yes, Clint?
I was just going to say, to understand this better, make sure you look at the numbers, which are showing like, here's, you know, section 3, 4, 5, and on the right-hand side, like the number 5,
yeah,
simply stays close to the initial position of trench. So the trench is actually moving to the left.
Yes. So now, does this happen? And the answer is yes. And how do we know it's happening? Well, because the Atlantic Ocean is opening and the Pacific Ocean is shrinking. That's kind of interesting, because the Pacific Ocean is by far the largest ocean, but it's getting smaller all the time. So the Atlantic Ocean is opening by about 1 to 2 centimeters a year, and this means the Pacific Ocean is shrinking at a similar rate. And because the Pacific is surrounded by convergent plate margins, which dip away from the ocean, that means that those trenches have to migrate oceanward. So that's a demonstration of trench rollback. Okay, so that's what we mean by the trench suction force. And now Warren Hamilton was a very famous tectonicist, passed away a few years ago. And this was his representation of a subduction zone. Here is the actual slab sinking, and here it's sinking through the transition zone, the 410-kilometer discontinuity. But you see the way he's showing it's sinking, it's sinking at a higher angle than the actual dip of the slab. And here he's showing the slab rollback. So this is going to bring the continent towards the ocean. And we're seeing that in North America, that North America is moving west at a couple centimeters a year. All right. Now, one of the things that has to be considered is that the mantle discontinuities at 410 and 670 kilometers may impede convection, the sinking of the lithosphere, because there the mantle is getting denser and denser, and that's going to become more and more viscous. So this structure of the upper mantle that we know from geophysics, right, is this density of the surrounding mantle increases by 8% over this interval. So that, increasing density of the mantle and increasing viscosity will impede whole mantle convection at greater depths. And we see that in the kinds of earthquakes we see in subducted slabs. So here we're looking at the kinds of mechanisms. So the filled circles are extensional mechanisms. So if you can imagine if a sinking lithospheric slab was being, pulled, sort of sinking fast because of the difference in density, you would have extensional focal mechanisms. Whereas if subduction is being resisted by the surrounding mantle, you might expect compressional mechanisms. So these open circles suggest that there's compression all the way down, except at the very top in Tonga, but most of the other subduction zones have extensional focal mechanisms down to about 300 kilometers, and then they become increasingly compressional with depth. So how can sinking slabs pull the plate? Shouldn't they just break off and sink more rapidly through the mantle? And actually they do, and they can still provide the driving force for plate motions, right? So that's, we understand that if a slab's mechanically attached to a subducting plate, it can exert a direct pull on the plate. But even if it's detached and sinking, it will still exert a pull on the plate. And this is a paper, and they're showing the two different ways. Here we've got slab pull with an attached slab, not shown very well, but that's the slab pull. And here we've got a detached slab, but it's exciting mantle flow, and that's causing a bit of drag on the base of the overlying lithosphere. So it's also affecting mantle flow. So slab suction is partly caused by the fact that two things happen when you inject a cold lithosphere into the mantle. One is this is going to heat up, but the material around it is going to sink, and so is going to cool down. So this hot asthenosphere is going to slowly be cooled at the same time that this slowly warms up, and you're going to attach a viscous blanket to that sinking material. So it sort of just adds to the weight of the material that's sinking. All right, so we've talked about the slabs exerting 90% of the force that's causing the plates, and Conrad and Lithgow Bertolini a few years back calculated that slab suction and slab pull presently account for 40% and 60% of that 90%. So detached slab sinking, exciting surrounding motion in the mantle is causing about 40% of that, and 60% is actually attached slab sinking. All right. So one question might be, do subducted slabs penetrate the 670 kilometer discontinuity where we've got this big increase in density and viscosity? And sometimes it looks like it does. So this is a mantle tomography beneath North America down to the base of the mantle. This cold region is probably the old Farallon plate. You can see it's broken off, as we know, because it was subducted beneath, the ridge was subducted beneath California 20 million years ago or so, 30. And so that gap is responsible for that. Now, if we look at some other tomographic images, we get a very interesting range of behaviors of subducted slabs shown by these blue regions. So here's one beneath Central America. It looks like it just keeps going down. Those two dashed lines mark the 410 and 670 kilometer discontinuity. Here in Tonga, it looks like the slab goes down, flattens out at in the mantle transition zone, and then continues sinking below it. Here in Indonesia, it looks like the slab goes down and penetrates the discontinuity easily. Here in central, this one going across just south of Japan into China, the slab goes down very nicely and then flattens out underneath eastern China. Very interesting behavior. And up north, that behavior is a little bit different. It looks like it goes down, flattens out a bit, and then continues to go down. So at depth, we can't see the site. There's no seismicity, as you know, below 670 kilometers. So we're looking at the deeper structure of subduction zones, which we can only follow with tomography. Interesting. All right, so we've covered this. This is collision resistance, which is, where is that? Should be somewhere in here. Should be in here. Resistance along transform faults, we can't show that. That's in the plane. And then trench suction, we've talked about that. So the point is that the plates are not driven by asthenospheric flow, by mantle convection currents. Okay, and one of the things that makes us understand how wrong this picture is, which we continue to show to our introductory students, I guess because it's somehow satisfying even though it's wrong, it shows the asthenosphere flowing away from the ridge. Now in this situation, this is what the modern geodynamic interpretation of what's going on is. Basically the asthenosphere is doing nothing. The mantle, it's not doing anything interesting. All of the action is going on in the plate itself. Now this is an interesting idea. This is Alvarez's model for what's happening. Now, what you're seeing here is kind of a map of the Earth showing the continents: North America, South America, Antarctica, Africa, Asia, Greenland, North America, in a very interesting projection. And what he's doing is saying, look, the Pacific Ocean is getting smaller and smaller as the Atlantic Ocean opens, which means the asthenosphere has to be squeezed out. But where can it go? Because it's not going to be able to pass underneath the continents because they have these thick lithospheric keels. So the way it must be working is there must be some places where the asthenosphere can flow through and escape. And he looked at these and he goes, okay, there's one. The big one is here between Antarctica and Australia. That's where a lot of asthenosphere can flow. Maybe a little bit can flow through the Caribbean or through, between Antarctica and South America. but most of it must be flowing through this gap here. Interesting. And this is the way he drew Earth's convective regime. He draws it as layered convection, right? With the upper mantle convection being dominated by plate tectonics, and then something going on below the 670 kilometer discontinuity that's maybe not completely driven by plate tectonics, but the asthenospheric flow is actually toward the ridges. That one's at the mid-Atlantic ridge. And here's in the East Pacific rise. All right. So let's get back to this point. Does mantle convection cells drive the plates, or do the plates drive themselves? Which is the story I've been telling you so far. This is the story I'm trying to erase from your memory banks. And this is the story I'm trying to replace it with. So, a really interesting paper a few years back by Ueda and Forsyth, that's in your reading list, looked at, okay, whatever is going on, if we sort of look at the plates and measure their motion, their velocities against various parameters, we should be able to figure this out. So here are three graphs. Both of them, all three of them, plot velocity in millimeters per year, you know, on the x-axis. But the y-axis, this is the plate area. This is the percentage of the plate that's connected to a downgoing slab in a subduction zone. And this is the continental area of the plate. Okay, and so these are all of the different plates with their different velocities. And what you can see is the plate area shows no relationship with plate velocity. So their thought was, if the asthenospheric drag was driving the plates, the largest plates should move the fastest, and you don't see that. I mean, one of the fastest moving plates is the Pacific plate, but one of the smallest plates, the Cocos plate, is even faster. And then the Nazca plate moves pretty fast, but it's not very big. What he noticed was, if you look at the percentage of plates that are connected to a subducting slab versus velocity, all of the ones that are connected to subduction zones move fast, and the ones that aren't move slow. This was very striking, this difference between the fast-moving plates, which are always connected to subduction zones, and the slow-moving ones, which aren't. So this plate velocity shows a very good relationship between the proportion of plate margins being subducted. So the ridge push is also important, but it's a very small part of the overall motion. But they noted one caveat, that plates with significant proportion of continents are always slower. And that thought is, this is because there's more of a drag, because the keels, the lithospheric keels for these continental plates are always thicker, and that drag slows them down. So this is a very important study. Very simple, but very important. We don't really need to look at that too much. So these are the sections. What we want to do is not leave you with the opinion that there's only this kind of convection, plate tectonics convection, because there's also plume convection, right? We know that there's heat and material being transported from depth beneath places like Hawaii and beneath South Africa, but most of the convection of Earth is as a function of subduction. So there's actually two kinds of convection going on. You know, this dominant plate tectonic subduction dominated convection, and then this second order plume-dominated convection. And if you recall our first lecture, we talked about the fact that plumes, you see evidence of plumes on all of the active silicate planets. That would be Venus and Mars, but only Earth has plate tectonics. So these are numerical models for the second order convection associated with plumes. And plumes are of particular interest to a lot of people. So here's one that's rising, starts rising at 4 million years, and then 43 million years. Here's 83 million years. And this is what it might look like just before it erupts, reaches the base of the lithosphere, and you have a large igneous province erupting, right? Now, this is going to be very interesting in the next lecture when we talk about the Middle Cretaceous, when we have a huge increase in plume activity at the same time as the mantle reversals. And so the core is down here. And so the idea that some people have is that maybe magnetic reversals are somehow related to these plume events. And there's a very strong evidence for that in the mid-Cretaceous, which we'll get to next lecture. The problem is that this sequence, the way it's modeled in our present understanding, is it takes many tens of millions of years for a plume, once it starts at the base of the mantle, to reach the top of the mantle. And we'll see that in the mid-Cretaceous, the magnetic reversals and the increase in plume activity is almost simultaneous. So this is one of the ideas. So we're now looking at the base of the mantle, right? This is the core. This is everything up here is the lower mantle. And the geophysicists have identified a region called the D double prime layer. And the geochemists have gotten excited about this because they can link the start of plumes to this interface, this thermal boundary layer between the core and the lower mantle, so that this ultra low velocity zone is thought to be where plumes start to rise, sort of the nursery of plumes. So it's kind of a useful little piece of seismology you can inflict on your geophysical friends. So this summarizes the mantle convection that we want to talk about. We have the dominant subduction related and mid-ocean ridge related convective regime. And, the mid-ocean ridges are very shallow features, very passive expressions of where the plates are being pulled apart, and the lithosphere, the asthenosphere is rising and melting. And then your subduction zones are these broad regions that mostly power the plate tectonic engine, where you have masses of lithosphere sinking, in the Eastern Pacific and in the Western Pacific, right? And then on top of that, we have some mantle plumes, which are sort of a second order kind of convection. Hawaii is one of them, and, there's other ones. So that sort of summarizes our thinking about what drives the plate. I hope that it's a fairly complicated discussion, but I hope you get a feel for what we really think is driving the plates.